All right, here's the homework for section 6.2, where we either use disks or washers to figure out the volume of solids of revolution. This first problem's a little bit different. Lots of things you want to notice here. The first thing you want to notice is we're going to be revolving around the x-axis. So that's really important. The x-axis, that's that horizontal axis. So that means that we'll be integrating with respect to x. What that means is that this question will be more like the first two examples I did after the intro video and less like the last two examples I did. So we know we're going to be integrating with respect to x. So what that means is that our bounds of integration will both be x values. And for our curves, we'll have to solve them as y equals something, so that something can only contain the letter x. So this curve right here, y equals 6x squared, is already in the right format. It's exactly how we want it. And the other curve, kind of confusingly, isn't given until the end here. So it's sort of strange that they give you one of the curves and then they give you the two bounds and then they give you the other curve. I think they do that a few times throughout the homework. So don't let that throw you off too much. And I know it feels kind of weird to have y equals 0 be one of the curves. Really all that means is y equals 0 is just the x-axis. So the region that's bounded in this question will extend all the way down to the axis that we're rotating around. And maybe you might remember from the videos that what that means is that cross sections won't look like washers and they'll instead look like disks. So for this one, kind of instead of pi r squared minus pi r squared, it's just pi r squared. Or if you really want to do it using the washer method as opposed to the disk method, the inner radius will be given by this function right here. So it's just equal to 0. Hopefully that makes sense. For this second question, it's kind of the same idea in that we're going to be rotating around the x-axis. So again, horizontal axis, our variable of integration will be x. And again, if you graph these three equations right here, what you'll see is the region that is bounded by these three equations, it stretches down to the x-axis, and that's because y equals 0 is just the x-axis. So again, cross sections here will be disks as opposed to washers. Think pi r squared, not pi r squared minus pi r squared. So question 3. It's tempting to look at this question and see y equals 0 as one of the curves that bound the region. And remember that in question 1 or 2, we saw y equals 0, and that meant we had disks as opposed to washers. So you might assume that question 3 is kind of the same as 1 and 2, but it's actually totally different. In question 3, instead of revolving around the x-axis, like we did in 1 and 2, we'll be revolving around the y-axis. And the y-axis, that's a vertical line, so this will be more like the last two examples that I did as opposed to the first two examples that I did. Whenever you rotate around a vertical line, your variable of integration ends up being y if you're using the disk or the washer method. So since our variable of integration is going to be y's, we'll figure out our bounds of integration by finding two different y values. So this y equals 0 won't relate to the inner or outer radius, and instead this will kind of mark one of your bounds of integration. Your inner and outer radius, or radii, I guess, will be given by these two curves. And again, it's strange the way they list these. I wish they listed this one first and this one second and then this one third. But whatever, that's the order they list them in. This one and this one will correspond with your inner and outer radii. And I'll let you figure out which is which maybe by graphing this thing. And again, note, since our variable of integration is y, when you set up your integral, you're only going to want y's in your integral. So you'll have to solve the two equations that tell you your inner and outer radius for x, so that they're written in terms of y's. So over here, maybe you take the square root of both sides of the equation, and then over here it's already solved for x, so there's not really a whole lot to do. For question 4, we're back to rotating around the x-axis, which is kind of the easier case, the case that you probably prefer. And I like the order that these are all written in. We have some curves solved for y and some other curves solved for y. That's great. These will end up determining your inner and outer radius. And then we're given these two already solved for x, which will be our bounds of integration. So I think in this one, they kind of give you the bounds of integration and they give you the two different curves. And you'll note that one of those curves is itself the x-axis. So question 4 will be kind of like 1 and 2 in that it'll be the disk method as opposed to the washer method. Question 5, kind of more of the same. We're revolving around the x-axis, which is a horizontal line, and therefore our variable of integration will be x. So this will be the case that you like a little bit better. And note that again, that our two curves are given to us, and one of them is y equals 0, which is itself the x-axis. So this will be yet another case where we're doing the disk method instead of the washer method. I don't make these problems up. I kind of choose them from a larger library. And the library, the questions that were written in a way that was pretty similar to the way we've been presenting them and your book presents them, had a lot of disk questions and not so many washer questions. So if you're wondering why it turned out that way, that's why it turned out that way. Note they give you the bounds of integration right here in the problem, which is kind of convenient. Make it easier to set up your integral. Question 6, finally, I think you're going to use the washer method here. Let's see what it says. Find the volume formed by rotating the region enclosed by these two curves about the y-axis. So the y-axis, that's the vertical axis. So rotating around a vertical line like the y-axis means your variable of integration will be y. And if your variable of integration is y, what that means is that you're going to solve your two equations for x. So this equation is already solved for x and this equation is already solved for x. They kind of did some work for you already. Maybe you can graph this and this. And then this one's a little bit tricky with y greater than or equal to 0. All this is telling you is that your lower bound of integration is 0. So when you're graphing the three of these guys, maybe just type y equals 0 into Desmos and that'll help you figure stuff out. They don't tell you the upper bound, but maybe you can figure out when these two guys intersect and that'll help you figure out what the upper bound is equal to. And then 7 and 8 are kind of similar. They're the last two questions on the homework. They're pretty similar to the rest of the questions that you've done. Really what changes is instead of rotating around an axis, we rotate around a line. And I don't know if these switch, if some of you will get y equals and some of you will get x equals. I guess I can let you figure that out. But for my version of question 7, we're rotating around the line y equals 1. And what you need to know about the line y equals 1 is that it's a horizontal line. So since it's a horizontal line, your work here will be a lot like when you rotate around the x-axis. This is the case that you like. Our variable of integration will be x. We want to solve our curves for y. So this one is already solved for y. This one's not solved for y. So you could do some algebra to solve this one for y. And then our bounds of integration will be in terms of x's. So here's one of the bounds of integration. And maybe you can figure out the other bound of integration from these two equations. And one of the curves that we'd use to figure out the inner and outer radius, this y equals 1 right here, ends up being exactly the line that we rotate around. Again, I don't know if that'll happen for everybody or if that's just dumb luck in my version of the problem. But since one of the bounds is the axis of rotation, what that means is the bounded region will span all the way to the axis of rotation. So what that means is a cross section will be a disk as opposed to a washer. Question 8 is a lot like question 7, except one of the bounds is not the axis of rotation. So down here I got y equals x squared and y equals 1. And so maybe you can graph the two of those guys to get a feel of the bounded region. You can figure out the points of intersection to figure out where you're going to integrate to and from. And then what you're going to do is you're going to rotate that around the line y equals 6. I think what you'll see down here is that 8 is a lot like 7, except 7 you end up with the disk method and 8 you end up with the washer method. But since in this version, we're rotating around the line y equals 6, which is a horizontal line, my variable of integration will still be x. And that's it.